Hello, in this video we're going to go over a very interesting relation between the open sets of Rn and continuity and also closed sets of Rn. Okay, so here is the main theorem. We'll prove this one and then we'll do a couple of examples. Let f from Rn to Rm be a function. F is continuous, by which I mean f is continuous over its domain if and only if given any open subset U of Rm, the inverse image is an open subset of Rn. Just to remind you, the inverse image was all of the elements that are mapped to that set. So just as a reminder, inverse image of U is all of the elements of the domain that are mapped to U. So this was the definition. Same thing is also true for closed subsets. So f is continuous if and only if given any closed subset of Rm, the inverse image f inverse of C is a closed subset of Rn. Okay, so let's prove this one. So first we're going to do, because it's an if and only if statement, we'll have to do two different things. First, we're going to have to do the forward direction, which says if f is continuous, then f inverse of U is open for every open subset of Rn. So suppose f from Rn to Rm is continuous. So what we need to do is to show that in fact f inverse of U is open for every open set of open subset of Rm. So let U be an open subset of Rm. Now we're going to have to show that in fact f inverse of U is open. So how do we show something is open? We'll have to show for every element in that set there's a ball around it that is completely inside this set. So start with some element in the inverse image of U. So now what does it mean that something is inverse image? So we know what that means. It means f of x is in U, because x is already in Rn, so it means f of x is in U. So this is saying that f of x is in fact in U. Okay, so now we know that f of x is in U and U is open. So since U is open, there is some ball around f of x that is completely inside U. There is some positive real number r such that ball of radius r centered at f of x is completely inside U. Now it is time to use continuity of f. So since f is continuous, limit of f of x, or let's call this one maybe f of y, because I already have f of x here, as y approaches x is equal to f of x. Okay, because f is continuous. Now let's write down the definition of continuity. So that means there is some delta. So here I'm using the epsilon equals r in the definition. So there is some positive delta that if the distance between y and x is less than delta more than 0, then the distance between f of x and f of y, or f of y and f of x, doesn't really matter, is less than epsilon, which is r. Now, what does that mean? It means if x is in the ball of radius delta, or rather y is in the ball of radius delta centered at x, excluding the center itself, then f of y is in fact in the ball of radius r centered at f of x. Okay, now one thing is clear, that f of x is also in that ball. So clearly f of x is also in the ball of radius r centered at f of x. So this means if y is in the ball of radius delta centered at x, then f of y is in the ball of radius r centered at f of x. And what does this mean? It means f of y is in fact in U. But what we know is U is because this is inside U. This is a subset of U. So what does it mean? It means y is in f inverse of U. So what we showed is this. What we showed is that if y is in this open ball centered at x, then y would be in f inverse of U. And that by definition means ball of radius delta centered at x is a subset of f inverse of U, which means f inverse of U is in fact open. So therefore f inverse of U is open. Okay, so this shows that if f is continuous, then inverse image of every open is open. Now let's show the other direction. So we know that inverse image of every open is open, and we want to show that f is continuous. So let A be, let me start with assuming that f, assume inverse image of U is open for every open subset U of Rm. So this function f was from Rn to Rm. So the assumption is f inverse of U is open for every, it's very important that this is true for every open subset of Rm. Now we will have to show that f is in fact continuous. So let A be something in the domain. We need to show limit of f of x as x approaches A is in fact f of A. So what are we trying to do? The objective is to show that for every epsilon positive there is a delta positive, that anytime the distance between x and A is less than delta, the distance between and more positive between f of x and f of A is less than epsilon. Now if you think about this one, this is just the same thing as saying f of x is in the ball of radius epsilon centered at A. This one is the same as saying x is in the ball of radius delta centered at A. So these can be interpreted into, so this is f of x is in the ball centered at f of A of radius epsilon. This one is x is in the ball of radius delta centered at A. Now this guy is an open set, so we can take that and then do inverse image of that to get the value of x, because f of x being in some set means x is in the inverse image of that. Okay, so let's start with the epsilon positive. So let epsilon be positive. We would like to show the epsilon delta definition. Since ball of radius epsilon centered at f of A is open, its inverse image f inverse of ball of radius epsilon centered at f of A is open. Now we know that A is in this set, so we know A is in fact in this inverse image of ball of radius epsilon centered at f of A. How do we know that? We know that because f of A is in the ball of radius epsilon centered at f of A. Okay, so because of that and because of the fact that it's open, by definition of open, there is a ball around A that is contained inside this inverse image. By definition of open sets, there is, okay, so now I'm going to call the radius of that ball delta. There is delta positive such that ball of radius delta centered at A is completely inside F inverse of ball of radius epsilon centered at F of A. Now let's show that in fact this delta works in the definition of limit. So if x minus A is less than delta, and I don't even need to know, I don't even need to know x and A are different, so I don't need more than 0. Then what I get is x is in the ball of radius delta centered at A, which means x is in the inverse image of this ball of radius epsilon centered at F of A, which means by definition of inverse image, f of x is in the ball of radius epsilon centered at F of A, which means the distance between f of x and f of A is in fact less than epsilon. So let's see how we got to this. This is the definition of ball This one is because of this inclusion that I have here. If I call this a star, I'm using that. This one is definition of inverse image. And finally, this is the definition of ball. Okay, so what did I do? I showed that if x minus a in norm is less than delta, then f of x minus f of a in norm is less than epsilon. And that's exactly the definition of limit. So therefore, limit of f of x is in fact f of a as x approaches a. Thus, f is continuous at a. But this continuity is true for every a, since this is true for all a, f is continuous on its domain. So what we showed is that a function is continuous if and only if the pre-image or inverse image of every open set is open. Now we will have to do the exact same thing for closed sets, but that's not very difficult. What we do is that we're going to use the fact that complement of an open is closed and complement of a closed is open. So one thing to note is that if you take f inverse of a set complement, that's f inverse of that set complement. So if you use that, you would be able to recover the proof for this one. And what does that mean? These complements are actually quite different. So this one is f inverse of Rm minus a, and the other side is Rn minus f inverse of a. And this f was from Rn to Rm. So you use that, and with this you can get the proof of this one. So there is like some work to be done, but that's basically the idea. That use part A and use the fact that complement of open is closed, complement of closed is open. Okay, now let's see how we can use that in practice. Prove that the circle x squared plus y squared equals 1 is a closed subset of R2. So what we do is we take a function that is continuous and we describe this set as an inverse image of a closed set. So consider this function f from R2 to R defined by f of x comma y equals x squared plus y squared. Now this is a polynomial, therefore it is continuous. We had seen that before. So since f is a polynomial, it is continuous. Okay, now we know it's continuous, therefore pre-image of every closed set is closed. So the given circle is F inverse of 1. This is by definition of inverse image. Let's talk about that. So if you look at this, the set is all of the points x comma y in R2 that x squared plus y squared equals 1. And that's by definition exactly the values in the inverse image of singleton 1. Now, this singleton 1 is closed. This is a closed subset of R because its complement is negative infinity to 1 union with 1 to infinity, and we have shown that both of these two intervals are open. So now by the previous theorem, F inverse of singleton 1 is closed, and that completes the solution to this one. Much of the times in this class, when you want to show something is open or closed, you would use the previous theorem. Prove that every closed ball in Rn is a closed subset of Rn. We are going to describe this set using a similar strategy. So let R be a positive number and A be something in Rn. If you look at the closed ball centered at A, by definition, this is the set of all x in Rn such that the distance between x and A is less than R. So that's by definition. Now, let A be A1 through AN. So what does it mean that this distance, and this should be less than or equal to, this distance is less than or equal to R? It means a function that is defined by the distance must be less than or equal to R, and that can be related to inverse image. So define f from Rn to R by f of x equals the distance between x and A. Now, note that f of x is, if you write it down, you get square root of x1 minus a1 squared all the way to xn minus an squared. And this is continuous because it is a composition of continuous functions. Okay, so we know that inside is continuous because it's a polynomial, and we know that square roots are continuous as well, and the inside is never negative. Therefore, this is continuous. Now we are going to describe the ball as an inverse image. So the ball is the set of all x in Rn such that f of x is less than or equal to R. But what does that mean? It means it's the set of all x in Rn that f of x is in the interval negative infinity to R. Another way of saying that would be to say inverse image of negative infinity to R. And we know that interval is in fact a closed subset. So this is inverse image of negative infinity to R. Since negative infinity to R is closed, and this is something we have shown before, and f is continuous, by the previous theorem, f inverse of that set is closed. And that's exactly what we wanted to show. Therefore, the closed ball centered at A of radius r is closed. And that completes the solution to this one. So next time we're going to talk about compact subsets of Rn. So I will see you in the next video.